Welcome back to the lab. Welcome back to Eve for everyone. Today we're going to pick up our ESD Monitor series because this bench needs to get grounded. No, I'm just kidding. We're going to pick it up because we have something really exciting to talk about, and that's the schematic's finished. The schematic design is finished, and I'm super excited about that. So let's dive in and let's talk about that. Great. So we are in the schematic, and where to start? I guess the input voltage. So this design should work with a pretty wide input voltage, probably anywhere between 9 and 20 volts. I should really define that range, but it's designed for 12, and it's just a lot of the components support a larger voltage than that. And there's a couple things that we have. Sorry, I'm scrolling like a crazy person. So first of all, what we have is we have a 12 volt input, we've got a fuse, and we've got this filter with a ferrite bead. Probably could add a common mode choke as well. Perhaps I should add a common mode choke as well. However, that's not a component that's available off the shelf from my assembler. Let me check that. Okay, yeah, so they don't have any. Wow, they actually have some that you can. So they're their extended parts, so you can do it, but it costs you like $7 for a setup fee. That would be totally worth it if you're building this, because, wow, not complying with FCC regulations because you're radiating too much on your cable, not worth. Wow, yeah, I'm probably still not going to do it because I'm just building one for me, and I never intend to sell it, so just something to keep in mind. So we've got a power indicator on the output of that, ferrite bead, and this set to about 10 times more current than the design needs, but just really wanted to define a safe threshold with a fuse that should never, ever, ever blow. The most power-hungry component is this buzzer, followed shortly by our LEDs, so I think we'll be okay. Alright, let's walk through the outputs here. So for the mat, here's what we need. We need a place for the ground conductor to be attached to this board, the actual earth ground. Since the 12 volt input is isolated, we need to tie this back to ground. And so there's one terminal of this terminal block for that connection. And then there's a spare, because you've got two options. The first option is you can ground the mat on the same terminal block, but then you could actually have a broken wire from this design to ground and you wouldn't detect that. So basically, if the ground wire from earth to this circuit is broken, you wouldn't detect that because the mat would be floating along with your detector. So what I would recommend is that you take one of these blocks, tie it to ground, and then you have a separate path to ground through your ESD mat, and then you're checking that whole loop back through whatever it is, your grounding strip, your ground terminal of your power strip, the ground terminal ground wire actually through your wall. You end up testing that connection all the time. And then, of course, on the other side for the operator, we're using the tip switch to connect between the tip and the return. So basically, when you don't plug in your operator ESD strap, the switch itself will connect a 5 meg impedance across it, which should cause it to not beep at you. So if you unplug it, it'll stop monitoring, which is awesome, because I might want to unplug it sometimes. And that's a real use case if we just want the bench and we don't want the operator strap. So this will just give us a quick way to disable that. And I want to indicate this. I really want to indicate this. But I need to really think about what we'll see here, right? So for the test, it basically means we'll have what is that? Like 12 divided by 3 is 4 volts, so we'll have 4 volts on the output. Yeah, I don't know. We can't really drive a FET with that. We couldn't buy us a BJT with that because it's such a small current. Well, maybe we could. That'd be on the low end though. So we've got such large resistances at play here. By design. And speaking of, that's a good transition. Let's dive into this block, and I really like it. Basically, there are two identical hierarchical blocks, And what we've done is we've broken out the actual resistors for programming the threshold outside of the block so that we can program different thresholds if we want to have 2 or 3 or 4 copies of this in the same design. In this case, they're programmed to the same value, but that might not always be the case. So what I have is the math for what the thresholds is, and then in each of these designs, you can see that where we normally put that resistor, I just have the 2 terminals, so we can break it out to the outside of this hierarchical block, ultimately setting the high and low thresholds for the design. Pretty great. We've got a simple decoupling cap near each of the ICs, and honestly, there's really not a whole lot of capacitance on this board at all. Not that we really need it, but man, we should at least add a placeholder. I guess you're getting kind of a real-time schematic review, and man, I'm not doing great. You can tell this is in rough form. And one thing to keep in mind is this is an ESD monitor where there's expected to be ESD. And so there was a critical design decision around this test and return. And it was, do I add a TVS or no? And that's kind of a tricky decision because, well, TVSs have leakage current. And if I want to consider that leakage current in this design, that means that I need to have more current flowing through it. And if I have more current flowing through it, that means we might be passing more current through the user. That's not exactly great. Right now, what are we at for our default current? We've got 12 volts and 10 meg. So that's 1.67 microamps of current. That is not a lot. And that would be if there's a dead short between test and return. Given that we can expect at least an additional mega ohm, that means we are probably going to be in the realm of half a microamp. Maybe, something like that. We need to be a little bit careful with our leakage current. So what I opted for instead, to still protect this OP07, is given that we know there's only 2.2 nanoamps of input bias current, and that's the absolute maximum, I added a series 2K resistor and then a capacitor near the op amp. And now that's going to give this thing a delayed response. However, it's only an indicator. The ground strap should always be connected. It might be a couple seconds. Actually, it's a couple seconds. And the threshold that we're monitoring is a little bit higher. You got the amplification since it has a gain of 2. And ultimately what that drives to is a little bit of voltage error because of that 2.2 nanoamps. And we can calculate how much that is, right? It's nothing. I mean, it's 0 to 1, 2, 3, 4, 5, 6 significant figures. So I think we'll be fine. That's what that 2K resistor adds. And so basically what that's doing is that's giving us some ESD hardening. Because when you think about what ESD is, it is a high voltage impulse, and it's seeking a path to ground. Now, ideally, maybe this cap would be on the ESD side. You could argue that. So basically what I did is I added a series resistance and then an AC shunt to ground so that impulse can just go to ground. And that's the intent. It's not perfect because now this is an 0603 and ESD is a high voltage, so ESD could just arc across that resistor if it really wanted to. It's hard. I'd really need to do ESD testing to figure out if that worked. And I'd probably want to put a placeholder for a cap on the other side too. And this says it's own ESD hardening, but we don't want to blow out our op amp, so we really want to add something on the front end. We're probably going to blow up one of these boards over time. I'm just going to be honest with you. We're probably going to blow up one of these boards from ESD. That is not a perfect solution. And designing for ESD hardness, especially for something like this that's meant to be a monitor, it is a tricky mess of compromises. So we started with this. Maybe we need to get an ESD gun. How much do ESD guns cost? I'll think about that. That would be a fun little design exercise. Getting the ESD gun, zap it, and just see how that is. I like that idea. By the way, just so you know, this is gonna blow some minds. I'm just gonna walk you through the low level. So if we had a smaller resistance here, we could consider that an ESD connection to ground as well, because voltage sources are essentially a short to ground. Because if you're pushing current into a 12-volt supply, that needs to get back to ground, otherwise your voltage would go up. So functionally, you can consider that voltage rail as ground, because it's so close to ground, it will get there. However, that's not what we're doing. We're relying on the other conductor, this return path to ground, to be that 1 mega ohm to ground. And then on the other side, it's just monitoring whether or not you're connected to ground. So, something to think about. Let's move on. So the output of this buffer is basically compared with a couple comparators, open collector. It's actually double open collector because of those diodes. So we've got the open collector signal, and then we've got the diode pulling current through it. Then we've got that error signal, which is pulled up. All 4 of those tied together, coming over here to this gate with the buzzer. So if it's a high impedance or a low impedance, it will light the LED, it will sound the buzzer, and it will let you know that your conductor has broken. That's basically all there is to it. So, yeah, doing a non-inverting op-amp circuit with a comparator monitoring the value of that op-amp and a couple connectors going off board. One to get power in, and then we're going to space out those LEDs so we can fit our light pipes in the enclosure. Yeah, so I'm excited to see how this works. I'm excited to get this hardware in the lab, but there's one thing between us and hardware, and that is the PCB layout. Oh man, that was a little rough, and I should have really reviewed that schematic before we walked through it with you. However, sometimes just talking through your design is such a practical and effective method of schematic review. It is great to see just the little things that got exposed as we walk through this together. And it just really highlights the value of schematic capture, because when you're going through a design and you're managing a bunch of details, you miss details like that. Like, you miss the fact that the thing's going to beep at you until the end of time when you unplug your wrist strap, and that would be pretty annoying. So I'm really glad that we were able to walk through this together and really just talk through some of those nuances together. I think that's all we've got for today, but make sure that you stick around for the next one, because I'm really excited to walk through the layout. If you like this video and you can't wait for more, let me know by hitting that like button, getting subscribed, or leaving a comment down below. A special thank you to our Patreon members and YouTube channel members. I really appreciate the extra step that you've taken of supporting EE for Everyone directly. Thank you. Coming up soon, we'll be doing the PCB layout, and I'd say that we'll be getting hardware in the lab. However, we're going to pivot to one of our other series and get this hardware coming all at the same time. So it's going to be like Design City and then Hardware City, and I'm really excited for that. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thank you for watching EE for Everyone, and thanks for staying till the end. Bye!